All right, this brief tutorial will take place of the lab that we would have done if we didn't have a snow day for our first class. This assignment can be found in your supplemental packet that you purchased from the bookstore, and again, it takes place of the molecular models lab. The first model you're asked to build is one for CH4 or methane, shown here, and we can see the characteristic tetrahedral shape where each of these pairs of electrons has equal room between them. So the molecule is not a flat molecule, which we could draw on paper like an X, but indeed has this three-dimensional, sort of like a pyramid with a flag shape. If you'd like more information on some of these basic shapes, I'll attach a primer on Vesper, which gives you some basic explanation as to why these molecules are three-dimensional and not flat, but for your purposes of completing the lab assignment, that's not necessarily information you need to know. It's just this is our CH4 model with equal space between any of the adjacent pairs of bonding electrons. The second molecule they ask you to build is ethane with an A, and that has 2 carbons and 6 hydrogens, and we notice that they're all single bonds, each stick representing 2 pairs of electrons, and we can see that tetrahedral shape holds. It's almost as 2 tetrahedrons sort of pasted together. So again, it's not a flat molecule, but we can see how we can build chains by connecting the carbons. We simply removed a hydrogen that was here on each of the methanes and pasted the 2 molecules together. The next molecule they ask you to build is 1-butene, and the E in the word signifies there is a double bond, and the 1 signifies that the double bond is on the first carbon. So it doesn't matter mirror image where that carbon is, but the double bond comes off of the first carbon, and when we use double bonds, we end up removing 2 hydrogens. Normally there would be a hydrogen here and a hydrogen there, but each carbon still has its 4 bonds that it needs to be happy. 1, 2, 3, 4. This guy also has 1, 2, 3, 4, and so on. We can see that we have sort of a zigzaggy shape to the chain, but because there is rotation around the single bonds, we can actually get this double bonded segment to move in different planes. And I have a brief little video here that I'll show you so that you can see how the bonds can rotate about the single carbon-to-carbon bond. And you can notice here I can rotate it so I can make this top structure. I can rotate it again and make the first structure, and then I can rotate it and I end up with the structure over on your left. The next structure you're asked to make is cyclopentane. The A again signifies all single bonds. The cyclo is this circular arrangement of carbons. Pentane, pent tells us that we have 5. So we can see 1, 2, 3, 4, 5. And when we connect the carbons in a circle, we can see that we lose 1 hydrogen for each, so that we end up having 2, 4, 6, 8, 10 hydrogens for our 5 carbons. This ring structure becomes very significant in organic chemistry, in particular when you study benzene and other similar cyclic compounds that have alternating single and double bonds. For here, in this example, though, we just see alternating single bonds. Now, the reference sheet I gave you has an example and the rules for naming carbon compounds. If they're single chains, it's pretty easy. You just count the number of carbons, and you would look on the chart and find out what the name is. Especially if it's single bonds, it would be ANE, double bonds ENE, triple bonds YNE, and then you would have to tell the reader using numbers on the carbon chain where the double or triple bond is located. But we can also paste side chains onto a main group. And number 5 on your worksheet asks you to build ethyl cyclopentane. So the ethyl tells me that I'm going to have a 2-carbon subchain stuck onto my parent chain. The parent chain from our previous slide is this cyclopentane, And you can see I removed a hydrogen here, and there's a missing hydrogen here on my ethane. And what we're going to end up doing is pasting these two together to make ethyl cyclopentane. And we can see here is our ethyl cyclopentane. Now we don't have to tell the reader where this is, because no matter where we counted on this 5 carbon chain, this ethyl group would be located on the first carbon. By convention, you name the carbon chain, the parent chain, assuming that the junk or the side chain is hanging off the lowest number carbon. Now, if we had 2 side chains, another one hanging off over here, then we would have to tell the reader that it would be 1,4-diethyl cyclopentane. So you can use numbers to tell the reader where the chains or the double or triple bonds are, and you can use the prefix di or tri to tell them how many of those groups are. Remember, we can also get rotation around the single bonds, so this guy can actually be flipped over, and he'll look like this guy. So we still have the cyclopentane parent chain, we have the 2-carbon ethyl group, so these are identical chains just rotated around that single bond. So hopefully this gives you an idea a little bit about how to name carbon compounds. Again, the reference sheet I gave you has some of the prefixes and some of the nomenclature used, and the rule sheet I gave you gives you a step-by-step method to walk through how to identify these molecules by name. We look for the parent chain, we look for the junk, we identify at what number on the carbon chain the junk hangs off, and we reference that with numbers. So again, refer to the material that I've included on Blackboard, and hopefully this gives you enough of a feel for organic chemistry to not only complete the worksheet for Lab 40, but to be comfortable for those of you who go on to organic chemistry.